Hello! In this video, I'd like to cover the proof of a very unusual theorem, Kummer's theorem, which connects the prime factorization of the binomial coefficient with counting the number of times one has to carry when doing addition in base p. The binomial coefficients are a fruitful source of useful theorems in number theory. In my practical programming of Diophantine equations video, we used Lucas's theorem to get a handle on the binary digits of numbers. The digits of x are a subset of the digits of y if and only if y choose x is odd. But what if we wanted to know more about the divisibility properties of the binomial coefficients? Here I have the triangle of binomial coefficients, and I've highlighted those that are divisible by 2. And we can see a pattern start to form. This pattern is clearer when we plot more binomial coefficients. Here I've plotted up to row 500, and I've plotted various other divisibility patterns as well. Notice that the coefficients divisible by primes actually look quite nice. Prime powers are a bit less nice, and numbers with multiple prime factors like 6 or 10 look quite gross. So it's clear that there's some sorts of patterns going on. But how can we reason about these? I'll introduce the notation exp sub p of n to denote the largest k such that p to the k divides n. This is sometimes called the p-adic valuation, and it's simply the exponent of p in the prime factorization of n. The result by Kummer in 1852 is that the exponent of p in n plus m choose m is the number of carries when m is added to n in base p. In order to prove this result, I'm going to need another bit of notation. Let sigma sub p denote the sum of the digits function in base p. And let's actually start by looking at exp sub p, the power of p in n factorial. Since n choose m is built up out of factorials, this seems like a good place to start. For instance, suppose we want to figure out the exponent of 2 in 13 factorial. 13 factorial is, of course, just the product of numbers from 1 to 13, and each of these contributes some number of 2's to the prime factorization. The odd numbers don't contribute any, but 2 contributes 1, and 4 contributes 2, and 8 contributes 3, and so on. In order to add these up, I'm going to split apart these 2's like this, and we'll count them row by row. In the first row, we have a 2 for each even number between 1 and 13. There's 6 of them, which is 13 over 2 rounded down. In the second row, we have a 2 for each number divisible by 4 between 1 and 13. There's 3 of them, which is 13 over 4 rounded down. In the third row, we have a 2 for each number divisible by 8 between 1 and 13, and there's just the one 8, and 1 happens to be 13 over 8 rounded down, and that's it. There's no hope for any more. The numbers with 4 factors of 2 in them are going to be multiples of 16, and there are none of those between 1 and 13. And so overall, there's 6 plus 3 plus 1 equals 10 factors of 2 in 13 factorial. And this is the approach that I'm going to take when trying to figure out the exponent of p in n factorial. Right, I'll break each of the appropriate factors up, and then we're going to count them row by row. We'll count all the multiples of p from 1 to n, and then all the multiples of p squared from 1 to n, and so on and so forth. And when we add all of them up, we'll wind up getting the total number of factors of p in n factorial. So again, if we're interested in the exponent of p in n factorial, we need to look at how many factors of p each term of the product of numbers from 1 to n contributes. Each multiple of p between 1 and n contributes at least one factor of p. Some of them will contribute more than one factor, but again, we'll count those later in the subsequent rows. There are floor of n over p multiples of p between 1 and n, and so we'll start our tally of factors of p there. Next, let's look at multiples of p squared. Each multiple of p squared between 1 and n will contribute at least 2 factors of p, at least one more factor than the one that we've already counted. Again, some of these multiples will contribute even more factors of p, but we'll count those factors later. For now, we'll add in floor of n over p squared factors of p coming from the floor of n over p squared multiples of p squared between 1 and n. Next, we'll want to count the multiples of p cubed. Again, each of these contributes at least one new factor of p, and there's floor of n over p cubed of them. If we keep going, we'll eventually count all the factors of p, and the total we get is the sum over I of n over p to the I rounded down. You can take this sum from 0 to infinity, but eventually, once we pass the largest power of p less than n, all the terms of this sum are 0, so this is really a finite sum. This formula is known as Legendre's formula, but we can actually rewrite this sum to make it nicer. In order to evaluate the sum of the floor of n over p to the I, it'll help to write our n in base p. Let the coefficient of p to the I be a sub I. Then we can really easily calculate the floor of n over p just by removing the remainder when we divide by p, the a0, and removing 1p from each of the remaining terms to get a sum that looks like this. For the floor of n over p squared, again, we remove the remainder when we divide by p squared. In this case, it's going to be a sub 1p plus a sub 0, and remove 2 p's from each of the remaining terms to get a sum that looks like this. And so on and so forth, until we reach the last term, the floor of n over p to the I, where I is the highest exponent of p, and that's just going to work out to a sub I. Now, we want to take this sum, and if we add it up column by column, it works out quite nicely. If we add up this first column, this is a sub I times a finite geometric series, which works out to p to the I minus 1 over p minus 1. If we add up the next column, it's a sub I minus 1 times p to the I minus 1 over p minus 1, and so on and so forth. For a sub 2, it's a sub 2 times the finite geometric series, p plus 1, which is p squared minus 1 over p minus 1. For a sub 1, it's p minus 1 over p minus 1. And finally, I'm actually going to want to include an a sub 0 term in here, following the same pattern, a sub 0 times p to the 0 minus 1 over p minus 1, which is of course just 0, but it's a 0 with a purpose. Now we can rearrange this sum of fractions, and we get this expression here, which is just n minus the sum of the digits of n all over p minus 1. This formula for the exponent of p in the prime factorization of n factorial is also sometimes known as Legendre's formula, and it set us up to be able to calculate the exponent of p in the binomial coefficients. To calculate the exponent of p in m plus n choose m, let's just break up m plus n choose m into m plus n factorial over m factorial times n factorial. This fraction is going to have some number of factors of p coming from the numerator, and then we have to subtract off the number of factors of p from the denominator, both the factors of p that show up in m factorial and in n factorial. Using Legendre's formula, this gives us this, which we combine some fractions, gives us the sum of the digits of n and the sum of the digits of m minus the sum of the digits of n plus m all over p minus 1. This formula here gives us the number of carries when we add n and m together in base p, and let's see why. For the moment, I want to work in base 10 just to be most comfortable, but of course the theorems in this video only work when p is prime, and it's worth taking a moment to figure out where these proofs make use of that, where they fail when p isn't prime. Suppose we have an addition problem with no carrying. each digit in the result is the sum of the corresponding digits in the addends. So the sum of all the digits in the result is the sum of all the digits in the addends. Now suppose we do an addition problem with carrying, 123 plus 457. If we just add along each column, the digit sum of the result is still the sum of the digits of the addends. If we kind of leave 3 plus 7 as 10, as opposed to doing the carrying yet. So now let's see what happens when we fix this 10 as a digit by carrying. Well, we need to subtract 10 from the ones digit of the result and carry a 1 into the tens place. And of course, subtracting 10 from the ones digit will subtract 10 from the digit sum of the result. But we need to remember to actually carry. That extra 1 adds into the tens place of the result, adding 1 back to the digit sum of the result. So overall, when this carry happened, we subtracted 9, our base minus 1, from the digit sum. And so hopefully it makes sense that the digit sum of the addends is going to be 9 times the number of carries more than the digit sum of the result. And then if you solve that, that tells us that the formula that we had on the previous slide is exactly the number of carries. And formalizing this argument really isn't that bad. You just have to give names to everything, right? Call the digits of the addends a sub I and b sub I, and the carry bits c sub I, and the digits of the sum, let's say s sub I. Then the p to the i-th digit of the sum is just the sum of the p to the i-th digit of the addends plus a carry bit if we carried into this place, minus p if we had to carry into the next place. And then if we add up this equation over all places I, we get that the sum of the digits of the result, the sum of the s sub i's, is the sum of the digits of the addends, the sum of the a sub i's, and the sum of the b sub i's, minus p minus 1 times the total number of carries, the sum of the c sub i's. So this is a real surprise. I never expected there to be a formula for the number of carries when adding numbers. And as far as I know, this only works in prime bases. And it's really not that bad of a formula. The binomial coefficient is quite nice, although the exp sub p function is a little esoteric. But still, if you need to get a handle on the number of carries when adding, this might be the tool for you. Or vice versa. Suppose you wanted to know what 12 choose 5 was. Well, if we add 5 and 7 to get 12 in binary, we get 3 carries. So there's a factor of 2 to the third in there. If we add 5 and 7 in base 3, we get 2 carries. So there's a factor of 3 squared in there. If we add 5 and 7 in base 5, or base 7, we have 0 carries, so there's no factors of 5 or 7 in there. And finally, if we add 5 and 7 in base 11, we have 1 carry, so there's an 11 to the first in there. Any higher prime numbers, and 5, 7, and 12 will all just be digits in that base, so we won't get any carrying for higher prime numbers. So 12 choose 5 is 2 to the third times 3 squared times 11, or 792. There's 2 really useful corollaries in the case where p equals 2 that I'm going to want to make use of in the other videos in my Hilbert's 10th problem series. I already used the corollary that y choose x is odd if and only if the binary digits of x appear as a subset of the binary digits of y. Right? If there's no factors of 2 in y choose x, there can be no carries when adding x and y minus x in binary. And that only happens if those numbers are disjoint. It'll also be useful to consider the exponent of 2 in 2n choose n. Plugging into our formula, we get twice the digit sum of n minus the digit sum of 2n all over 1. But the sum of the digits in binary of n is the same as the sum of the digits in binary of 2n. So this cancels down to just the sum of the digits in binary of n. Put another way, when adding n to itself in binary, each 1 in the binary expansion of n causes a carry. This will give us a really nice handle on the sum of the digits in binary function in some videos to come. I hope that you'll join me for that. In the meantime, thanks for watching. Please leave any questions or comments below and be kind to each other.